Welcome to The Explainer. Today, we're diving deep into one of the most fundamental challenges in artificial intelligence. How do you make a smart decision when you just don't have all the facts? We're going to break down the mathematical engine that lets an AI reason, not with black and white certainty, but with calculated degrees of belief. All right, here's how we're going to tackle this. First, we'll get into why simple logic just doesn't cut it in the real world. Then, we'll learn the language of probability, see how the famous Bayes rule lets AI learn from new evidence, and then scale that up to build these incredible, complex models of the world. And finally, we'll see where this all comes together in real life. So, first things first, an intelligent agent, whether it's a robot or some diagnostic software, it has to operate in a world that is messy, ambiguous, and almost always incomplete. So how can it possibly navigate that? Well, it definitely can't rely on simple if this, then that rules.
I mean, we face questions like this all the time, right? You have one piece of evidence, a symptom, and it points toward a conclusion, but it's no guarantee. Well, AI agents face the exact same challenge. Whether it's a system trying to make a medical diagnosis or a self-driving car trying to figure out what its sensors are seeing, it's all about plausible, probabilistic guesswork.
The old way of thinking about AI used these really rigid logical rules, like if a patient has a toothache, then the problem is a cavity. But that's incredibly brittle, isn't it? What if it's gum disease or an issue with a filling? You'd end up with a crazy, complex web of rules that would break constantly. The modern approach, the much more robust approach, is to quantify our belief. We say, okay, the probability of a cavity, given the evidence of a toothache, is maybe 0.8 or 80%. That little shift totally changes the game. It acknowledges the uncertainty and gives us a flexible, realistic way to reason.
Now, what's really interesting here is how we can actually formalize uncertainty. It's not all just one big fog. On one hand, you have what's called aleatory uncertainty. Think of this as pure inherent randomness. It's like rolling a die. No matter how much more information you get, you can never know the outcome for sure. But on the other hand, you've got epistemic uncertainty, which is really just about a lack of knowledge. This is the kind of uncertainty we can reduce by getting more data. So one is about chance, the other is about ignorance, and a smart AI has to be able to handle both.
So, if we're going to deal with all this uncertainty, we need to form a way to represent it and to reason with it. And this isn't a job for simple logic. It requires a whole new language, the language of probability theory.
And it all starts with something called a prior probability, written as P of A. This is basically our baseline belief in something before we see any new specific evidence. It's our starting assumption. So for a fair coin, our prior probability of it landing on heads is 0.5. It's our initial hypothesis about how the world works.
But here's the thing, right? We're almost never operating in a total vacuum. The world is constantly feeding us new information, new evidence. The real magic of an intelligent system isn't about having perfect starting assumptions. It's about being able to systematically and rationally update those beliefs as new information comes flooding in.
So how do we actually do that? Well, we're about to meet the elegant, incredibly powerful mathematical tool that makes this whole updating process possible. Honestly, this is the engine that drives so much of modern probabilistic AI.
Okay, let's make this totally concrete with a classic example. You wake up, you've got a headache. Your first thought might be, oh no, do I have the flu? What we want to do is calculate the probability of having the flu given the evidence of a headache. And this simple question is a perfect showcase for how our own intuition can sometimes lead us way off track.
To answer this properly, we need three key pieces of info. First, P of H, the prior probability of just having a headache on any random day. Let's say that's 10%, or 0.1. Second, P of F, the prior probability of having the flu. The flu is pretty rare, so let's say that's 1%, or 0.01. And third, and this is a big one, P of H given F, the probability of having a headache if you know you have the flu. We'll say that's high, like 90% or 0.9. This term is called the likelihood. It basically tells us how well our theory, having the flu, explains the evidence we're seeing.
And the solution to putting all this together is Bayes' rule. It's this beautiful formula from the 18th century, and its real power is that it lets us formally flip the script on our reasoning. We can start by observing an effect, the headache, and use it to calculate the probability of its cause, the disease. This is fundamentally how doctors and detectives and scientists think, and Bayes' rule gives us the math to actually do it. The rule tells us exactly what to do. We take the likelihood of the evidence, that P of H where F, which is our 0.9, and we multiply it by the prior probability of the cause, P of F, which is our tiny 0.01.
Then, to get our final answer, we just normalize all of that by dividing by the overall probability of the evidence itself, P of h, which was 0.1.
And when you run the numbers, what do you get? Just 9%. Now, that might seem really, really low, right? Especially when we said that 90% of people with the flu get a headache. But it makes perfect sense when you stop and think about it. Headaches are pretty common, but the flu is pretty rare. So your headache definitely makes the flu more likely than its 1% base rate, but it's still far from a sure thing.
So Bayes' rule is awesome for one cause and one effect. But what happens when you're dealing with the real world, which is this tangled mess of interconnected variables? Well, for that, we need a much more powerful tool for modeling complex systems.
And the answer is something called a Bayesian network. You can think of these as visual maps of probabilistic relationships. Each little circle or node in the graph is a variable, and the arrows between them show how they influence each other. They give us this really compact, intuitive way to actually see the structure of a complicated problem.
Now, the secret sauce that makes these networks computationally possible is a concept called conditional independence. So, as the slide shows, if we know the alarm went off, the fact that John calls tells us absolutely nothing new about whether Mary will call. Once we know their common cause, the alarm, the two effects become independent of each other. And this trick allows us to simplify the math a lot.
So you can see how we can scale this up. We can start with a really simple model like the one on the left, where a single alarm causes two separate effects. But the real power is when we build this out into a much more realistic scenario, like the network on the right. Here, we can model multiple things that could cause the alarm, and then trace out all the downstream effects.
And this is where it gets really cool, because this network actually encodes our causal understanding of the world. A burglary or an earthquake can cause the alarm. The alarm then causes John and Mary to call. By putting probabilities on each of these steps, the network can perform some really complex reasoning. For example, it can work backwards and calculate the probability there was a burglary given only the evidence that both John and Mary called.
Okay, so we've got this powerful framework for representing and reasoning with uncertainty. So what? What does this all mean in practice? Why is this so transformational for AI? Well, this probabilistic approach is the backbone for a huge range of critical AI applications. In medicine, it's what helps a system weigh symptoms and test results to find the most likely disease. In finance, it's the engine behind systems that spot fraudulent transactions. I mean, it's used in everything from predicting stock prices to helping a robot decide its next move.
This quote really just nails it. The point is that AI has matured way beyond the brittle, black and white logic of its early days. To handle the real world's ambiguity, modern systems are built on these probabilistic models. They don't deal in absolutes. They deal in nuanced degrees of belief, which they can update whenever they see new evidence.
And the main takeaway for you is this: that mathematical framework, the ability to put a number on uncertainty and update your beliefs using rules like Bayes' theorem, that is precisely what allows an AI to navigate the messy, unpredictable world we live in and make smart, reliable decisions.
And that leaves us with a pretty big question to chew on. As these AI systems get better and better at modeling the world and weighing probabilities, often without the cognitive biases we humans have, what does that mean for our own role in making critical judgments in fields like medicine, law, and even public policy?